6C, sampling distributions and the central limit theorem. So up to this point, we've talked about data and individual data, and then we've done statistics with that. We've found the mean, the standard deviation. We've dealt with the distribution of that data and found probabilities associated with it, percentiles and quartiles and things of that sort. But we've dealt with the actual data. Now what we're going to talk about right now with a sampling distribution is we're going to talk about samples of data. We've seen this. A normal distribution with a mean and then a standard deviation. Right, mu plus sigma, mu minus sigma, and this was basically just a frequency distribution of our data values. But what we're going to look at now is instead of having this be the data values, we're going to make it a sample statistic. So instead of having a distribution of x, we're going to have a distribution of x bar. What does that mean? In the past, we've dealt with, if we were looking at the ages of students, we would do a distribution of their ages. Now, we take a bunch of samples of students and find the sample mean of the ages for each of those samples, and now we create a distribution of those sample means. So we're really starting to take parameters of statistics, or we're looking at populations of sample statistics instead of just populations of data or samples of data. Now, when we get into that, that's where we deal with central limit theorem. And we start taking populations of samples, or we start taking parameters of statistics, meaning that we are going to not just find the population mean of the data values, we're going to find the population mean of the sample means. We're going to find the population standard deviation of the sample means. Now remember, a population deals with all items of interest, whereas a sample is a subset. So what we're doing is we're finding all of the possible sample means of a sample of a certain size. Meaning if I take a class of 30 students and I take 5 students to create a sample and find their average age, then I have X bar, right? The sample mean of those 5 students' ages. Now, if I take every possible sample of 5 students and find each of their sample means, then I have the population of sample means. I have all possible sample means that could come from that population with that sample size. And this would say, find the population mean of those sample means. So average all of the sample means. This says find the population standard deviation of those sample means. And as I said, this is where central limit theorem comes into play. That central limit theorem tells us that the population mean of the sample mean, so if I average all of the possible sample means from some distribution, that is equal to the population mean. So if I take the mean of all the sample means, I'm going to get the population mean. If I take the standard deviation of all the sample means, central limit theorem tells me that I will get the population standard deviation divided by the square root of n, the sample size. So this right here is what central limit theorem tells me. The population mean of the sample means is equal to the population mean. The population standard deviation of the sample means is equal to the population standard deviation divided by the square root of n, where n is the sample size, as we've used in the past. So what I'm going to do here is I'm going to shift this around a little bit so we can play with it. See, I'm going to get rid of this top part here because I want the space. Now I'm going to rewrite this. So I'm going to move that over here and I'm going to call it CLT, central limit theorem. And I'm going to say mu of x bar is equal to mu, and sigma of x bar is equal to sigma over the square root of n. So I'm going to use this to just do some basic calculations to start with. Let's say we have a normal distribution where where mu is equal to 17.3, sigma is equal to 2.1. So we've got a normal distribution with a mean of 17.3 and a standard deviation of 2.1. And I want to take a sample of 7 items from this distribution, so a sample size of 7. Now, using the central limit theorem, I can now say that the population mean of the sample means is equal to the population mean, 17.3, and that the population standard deviation of the sample means is equal to the population standard deviation, 2.1, divided by the square root of n, the square root of 7, and quickly grab my calculator to do that. So we have 2.1 divided by the square root of 7. Gives us 0.79 approximately. So 0.79. Now, looking at that, we may notice something. We started out with a mean of 17.3. We kept a mean of 17.3. Remember, what we're doing here is we're doing the distribution of sample means. Our standard deviation went from 2.1 down to 0.79. Again, we're dealing with the distribution of sample means. And you may look at this, well, why did this get so small? What happened with my standard deviation? And here's the answer to that. When you are dealing with data, you have a spread of data. When you start dealing with means, now you have a spread of those means. Now, it seems like I'm being redundant here. But think about what the mean is. The mean is a measure of center, right? It has a centering function or action. Think of it this way. If I have a class of 30 students and 2 of them are over 6 feet tall, then the probability of me randomly selecting an individual who's over 6 feet tall would be 2 out of 30 or 1 over 15. Well, what happens if I take a sample of 5 people? What's the probability that their average height will be over 6 feet tall. Well, now you should start realizing, well, wait a second, only 2 people in the class are over 6 feet tall. Which means if I take a sample of 5 people, at least 3 of them are going to be less than 6 feet tall, possibly all 5 of them. So doesn't it make sense that it would be less likely that I'm going to find an average height that's over 6 feet tall than that I find an individual with a height that's over 6 feet tall? And if you think about that, yes, it does. So what's happening here is by taking the distribution of the sample means, we're actually shrinking down the width or the variation in our distribution. So our standard deviation is getting smaller. Well, let's put this to use then. Why do we care about this? Well, I said at the beginning of the course that the first 3/4 of our course was going to be dealing with descriptive statistics, describing the data that we're looking at. And then the last quarter of the course, the last 2 sections or topics, is going to be dealing with inferential statistics, taking the information we get from a sample and directing it to the population so that we can make decisions about the population. Well, what this is going to allow us to do is it allows us to look at samples and determine the likelihood that a certain sample will have a certain probability, that it will occur a certain way, which allows us to start saying, okay, if we get this for our sample, what does it tell us about our population? So let's take a look at this. So let's start out with, well, why not start out with something like this? So we'll stick with the population mean being 17.3, the standard deviation being 2.1, and when we take a sample, it's going to be a sample size of 7. And I'm going to ask the following questions. From this distribution, what is the probability that a random item selected from this distribution is greater than 18? So that's dealing with what we have asked thus far. Find the probability that the data value is greater than a certain amount, given a mean and standard deviation. At this point, since I'm talking about a single data value, we're not dealing with a sample size, we're dealing with one data value. So how do we find that probability? We say, well, let's find the z-score. The z-score is equal to x, 18, minus the mean, 17.3, divided by the standard deviation, 2.1, which gives us, looks like 0.7 divided by 2.1, so it should be 1/3. But just so that I don't say anything stupid, we'll subtract, 1/3 it is. So 0.33. Now, I rounded that to 2 decimal places because I'm going to now look this up in our table. So same table we've been working with. Sorry, I went out of view. So we're going to look at the same table, and we're looking for z is equal to 0.33. So remember, we go down the first column, we find 0.3. We go out to 0.03, and we get 0.6293. So 0.6293. That's from the table. So when z is equal to 0.33, we come out from the table, we get 0.6293. Remember, the table always gives us the area to the left. We're looking for the probability that x is greater than 18. So we're going to go 1 minus, right? Table gives us this area. We want this area. So that's 1 minus 0.6293, which gives me 0.3707. So 0.3707. So the probability that we randomly select an individual who is, or an individual item that is greater than 18 is 0.3707. So that's the probability that an individual item has a value greater than 18. Now what I'm going to do, and I'm going to change colors on this, and I'm going to erase this part here just to give myself a little more space. I'm going to ask the question, what's the probability if I randomly select a sample of 7 items that the average value of those 7 items is greater than 18? So we're no longer asking what's the probability that if we select a single item that it has a value greater than 18. We're asking the probability that if we select a sample of 7 items, that their average will be greater than 18. Well, that's going to change a couple things for us. We want to find a z-score, but now we're working with a slightly different calculation. So let me come over to this side here and say, well, if I want to find the z-score, we were looking at x minus mu over sigma, right? That's our z-score when we're dealing with this. But now we're actually looking for dealing with a sample. So we're not dealing with x, we're dealing with x bar. We're not dealing with mu, we're dealing with mu of x bar, the population mean of the sample means. And we're not dealing with sigma, we're dealing with sigma of x bar. So we're now looking at a sample mean and subtracting the population mean of the sample means, and then dividing by the population standard deviation of the sample means. Well, we know from central limit theorem that mu of x bar is equal to mu, and sigma of x bar is equal to sigma over the square root of n. So I'm just going to substitute those in and say, and actually I'm going to do it here to keep that space available, that it's equal to x bar minus mu of x bar is equal to mu. Sigma of x bar is equal to sigma over the square root of n. So now I have a new version of the z-score formula. It's not a different method. It's just that now x became x bar, mu of x bar took the place of mu, but that's equal to mu, so we're good there. And sigma of x bar took the place of sigma, so we get sigma over the square root of n. So we have a slight modification to it because we want to find the z-score of a population mean, not of a particular data value. So we can now find z. Z is equal to x bar is 18 minus mu, the population mean is 17.3, over sigma, that's 2.1, over the square root of n, which is 7. So we end up with this formula. Now, I will point out to you that this looks almost identical to the original formula because we just substituted in x bar of everything. But you could do the calculation separately. Say mu of x bar is equal to mu, so that's such and such. Sigma of x bar is equal to sigma over the square root of n, so that's equal to such and such. So you could get those two values on your own and then just plug them into this one. I have a tendency to like to just use this formula as it is and plug it directly in. So I do deal with one formula instead of having to do those transformations and then substitute that into that formula. So let's do this calculation. So again, 18 minus 17.3, and I'm going to write this off to the side of this one, so that's 0.7. And the reason I'm doing it is because I want to demonstrate the order that things have to happen. Be careful about order of operations. If you're plugging this into the calculator all in one shot, you better make sure that you do it correctly, otherwise you're going to throw off your numbers. So I have 2.1 over 2.1 divided by the square root of 7. So the square root of 7 is 2.65 approximately. So now I still have 0.7, but I'm going to take that 2.1 and divide it by the 2.65. Now I'm going to be honest here. I'm actually going to keep the full value that came out of my calculator. So the number that you get by taking 2.1 and divided by 2.65 may be slightly different. In fact, it will be slightly different than what I get by dividing 2.1 by the square root of 7, which gives me about 0.79. So 0.7 divided by 0.79, and again, I'm keeping the full value, so your number may come a little bit off, is approximately 0.88. So, most important thing with this, make sure you keep those order of operations going correctly so that you get the correct value. So now we get a z-score of 0.88. So I can look that up in the table. 0.8, I go over to 0.08, and I get 0.8106. Okay, 0.8106. Remember, this is not the z-score. That's the value that I pulled from the table when I looked up that z-score of 0.88. And remember, the table always gives us the area to the left. We're looking for x bar greater than 18, so we're looking for the area to the right. So we're going to take 1 minus that, which gives us 0.1894. Thus, the probability that our sample mean will be greater than 18 is 0.1894. So we see, and this fits along with what I was explaining about it making our distribution tighter, that the probability of randomly selecting a value greater than 18 was 0.37, or about 30%, 37% of the time we'd select something greater than 18, or 37% of the data is greater than 18. Whereas the probability of selecting a sample of 7 items with a value with a mean greater than 18 is only 0.1894, or about 19% of the items. So 37% of the items greater than 18, whereas only 19% of the samples will have a value greater than 18. So that's the process, and it's just plugging it in. Well, I'm going to add a couple more formulas over here because we have this z-score over here, and I'm going to write it down like this, plugging in the values. So I have z is equal to x bar minus mu over sigma over the square root of n. And let me get this out of the way so I can continue writing the next part, which you may see, well, what's the next part? We already have this. The next part is the reverse transform. Remember, we dealt with this thing that was x is equal to mu plus z sigma. Well, now I'm going to do the same substitutions in here and say that x is equal to mu of x bar plus z times sigma of x bar, which is equal to mu, because mu of x bar is equal to mu, or I should say x bar is equal to mu of x bar plus z times sigma of x bar. So x bar is equal to mu, because mu of x bar is equal to mu. You're seeing just the top of my head there, okay? So mu of x bar is equal to mu plus z times sigma of x bar is sigma over the square root of n. And you want to put those in parentheses so you can see it. So I'm going to write that over here, that x bar is equal to mu plus z sigma over the square root of n. So now we have a new reverse transform to take it from a percentile and bring it back into the sample mean. So let's do another example forward, and then we're going to do an example in reverse. So I'm going to get this stuff out of the way over here. I see it as being unnecessary at this point in time. And let's go back to IQs. We know that with IQs, that the population mean is 100 and the standard deviation is 15. Now, I don't know if you're familiar with a little group known as Mensah. Mensah is basically an IQ society. They're smart people, and they want to know that they're smart, and they want other people to know that they're smart. To get into Mensah, you need to be in the top 2% of IQs. You have to be in the top 2% of IQs. So if you're in the top 2%, that puts you on which side? That's here, right? The top 2%. Remember, everything we deal with at this point deals with the left-hand side, so that means another 98% must be below you. So to be in the Mensah, you have to be smarter than 98%, or you have to be in the 98th percentile. You have to be smarter than 98% of the population to get into Mensah. And that's relatively distinguishing, right? That means that only 1 in 50 people qualify for Mensah. If you're the top 2%, that's 2 out of 100, 1 out of 50. So 1 in 50 people qualifies for Mensah. So let's use this information and go through it forward, dealing with central limit theorem, and then go through it backwards. In fact, we're going to do both the standard setup and using central limit theorem. First of all, dealing with IQs, ignoring the Mensah part of it, what is the probability that we randomly select a person whose IQ is greater than 120? So the probability that we randomly select a person whose IQ is greater than 120. Well, we're going to find our z-score is equal to x, 120, minus mu, 100, over sigma, 15, which gives you 20 over 15, or 4/3. Okay, so 4/3, so that's 1.33. So that's our z-score. We go to our table and look up 1.33, and we get 0.9082. We're looking for x to be greater than 120. So we're looking for the right-hand side. Remember, our table always deals with the area to the left. So we're going to take 1 minus that, which gives us 0.0918. So the probability of randomly selecting an individual with an IQ greater than 120 is 0.0918. So that would put them in approximately the top 9% of the population. They're smarter than about 91% of the population, which means they don't qualify for Mensah. Just to put it out there. Okay? What is the probability that if I take a sample of 10 individuals, that their IQ will be greater than 120? Well, z is equal to x bar is 120, minus mu, 100, over sigma, 15, over the square root of 10. So I'm just going to quickly go through that with the calculator. So 120 minus 100 is 20, of course. We want to take the square root of 10, so just to double check my number. So I came up with 0. No, not 0 point, that's, I think this is why I double checked it, 4.22 approximately. 4.22. Well, if you think about it, that's a high z-score, right? We're more than 4 standard deviations above the mean. So if we look up 4.22 in our table, we find 3.7 or more gives us 0.9999. We're looking, and that's the area to the left, so the area to the right would be 1 minus that, or 0.0001. So the probability that a sample of 10 individuals would have an average IQ greater than 120 is 0.0001. So about 0.01% of the samples that we would take would have an IQ greater than 120. Remember that our mean is 100. If we're taking a sample, we're centering that. So even though about 9% of the population has an IQ greater than 120, only 0.01% of the population of samples of 10 individuals would have an IQ greater than 120. Well, let's go the other way and look at it and say, okay, so what IQ do I need to get into Mensah? So we're going to reverse this process and say, and I can leave this here, that's good. I'm just going to switch the color of my marker. If I start with the top 2%, which gives me the 98th percentile, what data value do I need, or what IQ do I need to qualify? So that's where we come into our reverse transform. But to do that, we're going to need to find z. And remember, that's how we did a reverse table lookup. We have 0.9, well, we have 98%, the 98th percentile. that means we're looking at 0.9800 as the area to the left of that value. So I'm going to look at my table. In the body of the table, right, this area, not off to the side, that's z-scores only. I want to find the z-score by looking in the center of the table. So I look in here, I'm looking for 0.98, and the closest thing I get is 0.9798, 9798, which gives me a z-score of 2.05. So I have a z-score of 2.05. So now I have the z-score, I have mu, I have sigma, I have my sample size, I have z, I can find out the mean, or the sample mean. Well, actually, where am I going with that? I want to get back into I'm up here. Actually, I'm not even that, I'm in the basic thing of, let's plug it into our reverse transform. So x is equal to mu, 100, plus z, 2.05, times sigma, 15. Remember, we're looking for what IQ does an individual person need. So plugging that in there. So remember, order of operations says take 2.05 and multiply it by 15, then add 100. And that gives me 30.75. So 100 plus 30.75 is 130.75. And since we're talking about IQs, we would say that that means we would need an IQ of 131 to qualify for Mensah. Well, what about if I'm dealing with a sample of 10? What average IQ would my sample need to be in the top 2%? Now, technically that's no longer, well, I guess we could say that is still fitting into Mensah's top 2% of IQs. If you want to look at a group, what would their average IQ need to be to show that that group on a whole qualifies for Mensah? Obviously, there could be individuals in that group that do not, but you could have certain ones that compensate for that. So in that case, we're looking at x bar is equal to 100 plus z, 2.05, times sigma, 15, over the square root of 10. So 15 divided by the square root of 10 gives us 4.74. We multiply that by 2.05, give us 9.72. So therefore, 109.72 would be the average IQ necessary for a group of 10 individuals to create a sample that is in the top 2% of IQs for a group of 10 individuals. So this one here, x, we're finding the value, the actual IQ necessary to get into Mensah. Here we're saying if we took a sample of 10 people, what would the average IQ need to be in that group to have it be in the top 2% of the samples? And we see that that group would have to have only an average IQ of about 110, as opposed to the 131 that one person would need. And that's dealing with central limit theorem. Key things, we're taking population means of sample means and population standard deviations of sample means. these two pieces here and these two formulas here, where now z is equal to x bar minus mu over sigma over the square root of n, and x bar is equal to mu plus z times sigma over the square root of n, these are going to be key pieces of topics 7 and 8. So basically for the rest of the semester. So you want to make sure that you understand those and you can use those. Okay? And this allows us to now deal with sample means and look at the distribution of sample means and find the probability that a sample mean will be greater than a value or less than a value or between two values, or what percentile or what sample mean would be necessary to be in a certain percentile.